Let's take a moment to think about how humans recognize images. When you look at a photo, your brain processes it in layers. You might first notice basic shapes or edges, then patterns, and eventually you understand what you're seeing: a dog, a building, a face. Convolutional neural networks, or CNNs, are designed to work in a similar way, and they've become one of the most powerful tools in the world of artificial intelligence for tasks involving visual data. Unlike traditional neural networks that flatten images into long rows of numbers and treat all inputs equally, CNNs maintain the spatial structure of an image. They understand that pixels close to each other are likely related, and they process images in layers that progressively learn more abstract and meaningful features. A CNN starts with a convolution layer, which acts like a scanner, moving over the image in small windows to identify local features like edges or corners. These filters, or kernels, are shared across the image, meaning the model doesn't need to learn a unique weight for every pixel. This makes CNNs far more efficient for image data. After this, we pass the output through a ReLU activation, which introduces nonlinearity, helping the model capture complex relationships rather than just straight lines. Then comes the pooling layer, which essentially compresses the image by keeping only the most important information, making computation faster and reducing the chance of overfitting. Once the image is processed through these convolution and pooling steps several times, the CNN flattens everything and feeds it into a fully connected layer. This is where the actual decision happens. Finally, the model uses something like a softmax function to convert raw scores into probabilities, like, this is 85% likely to be a cat. This architecture makes CNNs incredibly effective. For example, an insurance company might use a CNN to analyze photos of car accidents. Instead of sending each claim to a human adjuster, a CNN could automatically detect if the damage is minor, major, or a total loss, making claims processing faster, more scalable, and less prone to subjective judgment. The power of CNNs lies in their ability to automatically learn the right features without human intervention. In traditional systems, someone would have to handcraft rules to detect shapes or corners. But CNNs do all of that themselves. You feed them images, and they learn the rest. Of course, this comes with challenges. CNNs need a lot of labeled images to learn from, and training them is computationally expensive. You'll usually need specialized hardware like GPUs to do it effectively. They're also harder to interpret. Once a model makes a decision, it's not always clear exactly why. Over the years, researchers have developed many famous CNN architectures. LeNet-5 was one of the earliest, used for digit recognition. AlexNet made headlines in 2012 by outperforming everyone else in a major computer vision contest. Then came VGGNet, known for its simplicity and depth, ResNet, which solved the problem of training very deep networks by adding shortcut connections, and EfficientNet, which smartly scales models to improve both speed and accuracy. CNNs are now used everywhere, from facial recognition on your phone to analyzing medical scans, helping autonomous cars see the road, and even reading handwritten documents. In essence, CNNs have given machines a form of visual understanding. They're not just seeing pixels, they're learning to perceive the world in a structured, layered way, much like we do. And in a data-driven age where images, video, and visual content are everywhere, this capability is nothing short of revolutionary.